Welcome back to COS 302. Today we're going to be talking about systems of linear equations. To start off with, let's talk about what a linear equation is. A linear equation is an equation that is linear in its variables. So typically we would write something like this: a1 x1 plus a2 x2 out to some number of variables, some number of terms, say an xn, and then we would make this equal to some constant, typically b. We refer to these guys, the x's, as the variables, and we would refer to the a's as the coefficients. It can be helpful to think of linear equations as generalizing lines, so lines and planes and hyperplanes and objects like that. In 2 dimensions, an equation might look something like this. If we have dimensions, let's say this is x1 and this is x2, then a linear equation might give us a line that looks something like this. Maybe this would be something like, say, x1 minus x2 equals 2. When we talk about systems of linear equations, we're talking about collections of linear equations, not surprisingly, and so we tend to use a little bit of a larger indexing scheme to represent the fact that we have m equations, each with n variables. So we might say a11 x1 plus a12 x2, and so on, out to, say, a1n xn, and then we also give the b a subscript in this case. And we might have some set of these, say m of them, so then we would have a m1 x1 plus a m2 x2, and so on, out to mn xn, and then of course bm. Now the name of the game is to try to find x's that satisfy these equations altogether for particular values of a and b. Generally speaking, there are 3 kinds of situations that can arise. One is where there are no solutions, one is where there is an infinite number of solutions, and the third situation is where there is exactly one unique solution. It can be helpful to think of these in terms of lines again, in terms of intersections. So a situation where we have 2 equations and 2 unknowns, we would have 2 lines, and the nice place where we would have a unique solution is where those 2 lines intersect. So something like this, where the place where they cross is the solution. It's the point that satisfies both linear equations. A situation where there are no solutions might be where the lines are parallel. So perhaps we would have one line and then another line that's exactly parallel to it, such that it never intersects. That's a situation where there are no solutions. And then the third situation is where there's an infinite number of solutions. In this case, it's also where they're parallel, but now they're overlapping. Of course, I can't draw that very well, so let's just imagine that we're in a situation where one of them is right on top of the other guy. And so these are cartoons, or sort of abstractions of the 3 different situations we might have when reasoning about solutions. This is often called an underdetermined case and an overdetermined case. It's worth pointing out that these exact things don't necessarily generalize that well to higher dimensions. One example of this is if we think about in 3 dimensions with planes, we can have a situation where there are infinite numbers of solutions, but the things aren't exactly overlapping. So just to draw a picture of what I mean, you could imagine a situation where we have a plane reflecting one equation and then an intersecting plane, something like this, that's going through it. And in this case, the planes aren't exactly the same, but nevertheless, there's an infinite number of places where they intersect, this line here that's going through them. Unsurprisingly, we often like to write these kinds of things in matrix form. That's kind of the game of linear algebra. So our set of A coefficients stacked together into a matrix that looks like some, A1, 1 out to A1n, and then AM1 out to AMN. So we get a big matrix that is m rows and n columns, just like the way we have the A's arranged here. We would do something similar with the B's. make a big stack of B1 down to Bm, and of course with the x's as well, of which there are n. And this lets us write a complicated set of equations like this in a very simple piece of notation, which is, of course, we would write A matrix multiplied by the vector x equal to B. So this is a very dense compressed notation representing this big collection of linear equations. Having established what a system of linear equations is, then now we're going to talk about solving systems of linear equations. Sometimes we just say solving linear systems. Now, of course, in 2 dimensions and in simple situations, this is something that you've probably thought about for a long time, maybe since like junior high. We have 2 lines, maybe as before, we have an equation that looks like something like maybe x1 minus x2 equals 2. And then let's imagine that we have some other equation represented by a line. Maybe this is negative x1 minus x2 equals negative 1. So these lines are 2 equations. We can write that as a system. We would say negative x1 minus x2. So let's stack these equations on top of each other like we would when we solve a linear system. We would say negative x1 minus x2 equals negative 1. And then we would say here x1 minus x2 equals 2. Now, whenever you think about this from the point of view of kind of like high school algebra, right, you would solve for one of the variables and then substitute it in. It's worth thinking through what that process kind of looks like. And it turns out that that is essentially the same intuition for the linear algebraic procedure Gaussian elimination. So how does that work? Well, of course, given an equation, we can always add the same thing to both sides, or we can multiply both sides of one equation by some constant that's not 0. We could just add some number like 5 to each side of one of the equations, but that probably won't get us very far. But what we do is we observe that the equations themselves give us things that we can add and preserve equality. That is to say that we don't change the solution if we take one of the equations and add it to one of the other equations. So in this case, that's what we would do in our kind of high school algebra class, right? We would just add maybe equation 1 to equation 2. If we do that, we get another system of equations. Maybe we would keep the top one. So I'm transforming here. Maybe we would, and if we added these together, then the x1s would cancel out and we get a 0, and then we would get minus 2x2, minus x2 plus minus x2 equals minus 1 plus 2 equals 1. So if we think about this from a matrix point of view, where we're going to use the convention of sort of stacking the A and the B next to each other, then we would have started out with a matrix looking like this, right? We would have a negative 1 for that coefficient, a 1 for that coefficient, a negative 1 for that guy, and a negative 1 for that guy. We're going to do this thing where we draw the sort of vertical bar and then write the B vector, which in this case is negative 1 and 2. This kind of intuitive thing that we did just transformed this into a new matrix. So this became a matrix that is now negative 1, and 0, negative 2, with a bar 1, negative 1, 1. So we've already taken a step to make this easier because what we've done is turned this 2 by 2 matrix into an upper triangular matrix. And that's the kind of thing we're going to do when we solve larger systems of equations, is turn them into things that look upper triangular. So what would we do next in our sort of high school algebra class? Well, we would solve for x2, right? So we would do another transformation that corresponds to multiplying that row by a constant. In this case, we're going to multiply that row by negative 1/2 so that it cancels out the 2. So now we wind up with a negative x1 minus x2 equals negative 1 as before, but now we still have a 0 and we get an x2 equals negative 1/2. What did that do to the matrix here? Well, that made it somehow even easier. So now we have a situation where we have still negative 1, but now we have a 0 and a 1 here. And so we went from sort of annoying to a little bit easier because upper triangular, to upper triangular where we have a 1 on the diagonal. Now there are different steps that we might do next, but what I'm going to suggest is let's make it so that the other element of the diagonal is 1. So to do that, we would multiply this equation by negative 1. So we get a new system that is now x1 plus x2 equals 1, multiplying that by negative 1, and we still have 0 on the bottom, but we now have x2 equals negative 1/2. So in matrix form, we now have this situation. We have a 1, a 0, a 1, and a 1, 1 and 1/2, negative 1/2 rather. So this is a nice place to be. We now have 1s on the diagonal of an upper triangular matrix. And this is already in a form that we call row echelon form. I'll explain what that precisely means here in a minute when we talk about bigger matrices. In the final step though, what we're going to do now is we're going to get to a place where we have 1s along the diagonal and 0s off the diagonal. So turn that into an identity matrix. We can do the same kind of thing that we did before, same kind of rules, but now we're going to modify the top one again by subtracting the second one from it. So if we subtract x2 equals negative 1/2 from x1 plus x2 equals 1, then we get yet another system. But now it is x1 plus 0, and then we're subtracting negative 1 from 1, so we get 3/2. And then the bottom equation is x2 equals negative 1/2. And now we've solved the system, but just to complete the story, let's write this out in the actual matrix form. So now we have 1, 1, 0, 0, the identity matrix, and our solution on the other side. What we've done here with this step is we've turned it into reduced row echelon form. So reduced row echelon form. When we're solving a linear system with Gaussian elimination, what we're doing is trying to get it into reduced row echelon form, which is a natural generalization of the way that you might think about solving a small linear system like we did before, with, say, only 2 variables. The process of putting a linear system into reduced row echelon form will reveal whether it's the kind of system that has a single solution, or whether it has 0 solutions, or whether it has infinite solutions. So let's talk about row echelon form first. What row echelon form and reduced row echelon form are all about is the question of where are the zeros located. So first let's think about what kind of matrices we're dealing with. So we have matrices that are going to look like this, that have our coefficients for the A's and the B column vector. And when it's in row echelon form, then it's going to be upper triangular in this left part. So let's just let's imagine that we have some upper triangular matrix, and there's some other variables over here. So a key piece of terminology is that for every row, the leftmost non-zero value is called the pivot, or the leading coefficient. So in this case, that's this 5, this 4, this 3. These are the pivots, or leading coefficients. So the first property that we need for a matrix to be in row echelon form is that the pivot of a given row must be strictly to the right of the pivots above it. So this matrix is in row echelon form because the 4 is strictly to the right of the 3, and the 5 is strictly to the right of the 4. So an example of a matrix that is not in row echelon form might look like this. We might have some set of numbers across the top, and then rather than a pivot being strictly to the right, perhaps there would be a pivot that was immediately beneath the previous pivot. So this is not in row echelon form because this pivot, the 6, is not strictly to the right of the pivot that is this 3. So this is not row echelon form. The other requirement that we have for row echelon form is that if there are any rows that are all zeros, they must be on the bottom of the matrix. So what I mean by that is that if we have a row that is all zeros, it must be the bottom one. We can have other things, other places. This is in row echelon form because this, we have a pivot here, and then this 1 is strictly to the right, and then this row of zeros is at the bottom. An example of a matrix in which this would be violated that would not be in row echelon form might look like this. We have some row maybe halfway down like this. And so even though 5 is to the right of 1, this row of zeros is not at the bottom, and so it is not in row echelon form. Reduced row echelon form takes reduced echelon form a step further. Reduced row echelon form adds 2 additional requirements to row echelon form. First, each pivot must be 1, and second, each column containing a pivot must be 0 everywhere except for the pivot. What do I mean by that? One example might be if we had a 1, 0, 0, and then, so this is an example of a matrix in reduced row echelon form. There are 2 pivots. The pivots are this 1 and this 1. It is in row echelon form because this pivot is strictly to the right of this pivot, and the row with all zeros is along the bottom. This pivot has zeros everywhere else. This pivot has zeros everywhere else, and the pivots are both 1. So this is in reduced row echelon form. Now let's look at a couple of the counterexamples. We could imagine the same kind of matrix. Let's say 1, 0, 0, 5, 0, 1, 2, 0, 0. But now, rather than a 0, if we had a 1 here, now we have 3 pivots instead of 2. We have a pivot, pivot, pivot. They're all 1, and they're all strictly to the right of the pivot above them. So far, so good, except that this guy is not 0. So this pivot, which is 1, its column contains a non-zero entry other than itself. So this is not in reduced row echelon form. So given a matrix that is not in reduced row echelon form, how do we turn it into one? We do that by performing transformations of the rows of the matrix. And these transformations are exactly the same kind of transformations as we saw when we thought about simple 2x2 equations. So the allowed transformations, we can multiply the row by a non-zero scalar, and we can add any row to any other row. So we can use these transformations starting at the top row and going down to take any matrix and turn it into reduced row echelon form. Typically we would go down the matrix and scale and subtract to produce the upper triangular structure along with ones along the diagonal. Then we would go back through and remove the zeros above all of the pivots. A lot of machine learning is really about curve fitting, and it turns out that a lot of curve fitting is really about solving linear systems. So I thought I'd give you an example where solving a linear system corresponds to finding the coefficients of a simple quadratic fit to data. So here's the situation. We have a simple function. Let's imagine that we have some points that we've observed. So I'm going to imagine that there's some sort of horizontal axis z. I'm going to use z so that we don't get confused relative to the sort of x's and variables and things here in a minute. and then this is kind of f of z, the function that we're fitting. Let's imagine that we see 3 points. Let's imagine that we see the point -3, 1. Let's imagine we see the point -1, -1. And let's also imagine that we see the point 1, 5. And what we're aiming for here is to model these data with a line that hits all of them, that is of the form a z squared plus b z plus c. Now, the things we don't know here, just to be clear, are the coefficients a, b, and c. So from our point of view, what we're doing when we're going to solve the system is we're going to give these more conventional labels x1, x2, and x3. So in a curve fitting problem like this, what happens is each of the points, that is each of the data, they correspond to an equation. And so then what we're trying to do is find the coefficients that satisfy the data equations. So if we think about that, then what that means is that this is the value of z, and then that's the value of f of z. And so we can plug those values in and see what we get. So let's do that. So this point there, the -3, -1, so we would say, so that equation would be x1 multiplied by -3 squared, substituted in for the z, plus x2, -3, plus x3. And that equals 1. And of course, we can simplify this, and we get 9x1 minus 3x2 plus x3 equals 1. So that equation corresponds to that point. We could do the same thing for the other points. So this one, for example, we could see that that's going to be x1 minus x2 plus x3. So this has a 1 for its coefficient because it's -1 squared. But then bz, right, is going to be x2 times -1, so we get a negative x2. And then this is all equal to -1. Then this guy up here, this other point, that's going to be x1 plus x2 plus x3 equals 5. And this is, again, just because it's 1 squared plus 1x plus x3. Okay, so these are 3 equations that form our system of linear equations. This is a little bit funny because that doesn't look like a linear equation, but once we know z, it's linear in these x1, x2, x3. So now let's write out this sort of augmented matrix that represents this system of equations. We'll start with this one up top. So we're going to get a matrix that has a 9, and then a -3, and then a 1, and then a 1. And then for this equation, we're going to have a 1, and a -1, 1, -1. And then this equation is 1, 1, 1, 5. And so the way we would usually do this is we would put it in a bracket, and then I'm going to put a little line to indicate which coefficients are sort of on the left and which ones are on the right. So now let's go about the business of finding the reduced row echelon form for this. It's going to be multiple steps, but then ultimately once we get there, then we'll be able to read off the solution for what these unknowns are in a way that fits a quadratic to these data. So the first thing I'm going to do is try to make this value into 0. And the way I can do that is I multiply this whole row by -9 and then add to that the top row. So this is the common kind of thing, scale the row and then add another row. So if I do that, then the very first thing I get is, of course, I leave the top row where it is. So when I do that, then I'm going to get 0, 6, -8, 10. And of course the bottom row is still the same. So now I'm happy with the second row from the point of view of getting it into row echelon form. That is to say that the pivot 6 is strictly to the right of the pivot 9. Now I'm going to try to put a 0 in this location here. To do that, I'm going to do the same thing. I'm going to multiply the row by -9 and add the top row to it. As before, the top row stays, the second row stays, but now I'm going to get a 0 here, and then I get -12, -8, and -44. In order to finally get into row echelon form, then I need to remove this one and make it into a 0. It's helpful to note that, of course, I can divide all of these guys by 4. In this case, actually -4. Now I can multiply the bottom row by -2 and add the second row. So now what I'm trying to do is finally get it into row echelon form by eliminating this entry, and I can do that by multiplying this row by -2 and adding the second row. So if I do that, then as before, I keep the top row intact. Now I get a 0, and a -12, and a -12. And of course I can divide these by -12 and just get 1 and 1. So now we're in row echelon form, and we want to now get to reduced row echelon form. Good news, the bottom row already has a 1 for its pivot. So what we need to do now is get zeros above it. For the second row, I can do that by multiplying the bottom row by 8 and adding it. And for the top row, I can of course just subtract it directly. So I'll do both of those steps. Subtracting that gives me a 0. And here I get a 0. And this becomes an 18. This is still the same as it was before. Now notice here that I have a 6 and an 18, and so I can observe that I can make this a 1 and a 3. After I do that, I'm already happy with the second row as its pivot is a 1. After I've done that, I finally need to get rid of this entry here, and then I'll be nearly home. So I multiply this row by 3 and add it to the top row. Finally, I notice that the 9s can be divided by 9, giving me a very nice and simple form that tells me the answer. So, plugging this back in, I see now that this is x1 or A, this is x2 or B, and this is x3 or C. So now I can read off the overall equation and figure out what curve would fit through these. So that's going to be fz equals 1 multiplied by z squared plus 3 times z plus 1. So let's see if that makes sense. Let's plug in 0 for z. What do we get? We would just get 1, right? So let's imagine that point's right about there. Let's plug in -1, 1 minus 3 plus 1, hopefully is -1. Great. So if we plug in -2, then we see that that would be 4 minus 12, -8 plus 1, -7. So maybe that's down here somewhere. And then -3, that would give us 9 minus 9 plus 1. So that's good news. And then finally, let's look at 1. That'll be 1 plus 3, 4 plus 1 is 5. So we can feel reasonably confident that we have our quadratic that's kind of swinging down and up like that. So that was a situation where we had 3 data points and we were fitting a model that had 3 parameters. So I think you can see why in general in machine learning we're dealing with over-constrained systems. We have a situation where we maybe have a set of data, something, a cloud of data points, and some set of parameters that we're trying to fit. But the set of parameters in general won't fit the data perfectly. And so when we think about that kind of, solving that kind of linear system, then necessarily we're going to have to reason about what it means to approximately solve the system. In practice, what we often do is talk about the least squares solution, the one that is closest in a squared Euclidean sense, but we'll talk about that later in the course. I'd like to wrap up with another example of something like traffic flow as a linear system. So let's imagine that we have 4 intersections. Let's say A, B, C, and D, and each of these has some traffic flow. Maybe they're flowing into A and C, say, and we'll say it's flowing, we'll think of it as flowing out of B and D. Let's imagine that there's moreover some flow between these intersections. Something like that, maybe. And what we know is the flow into and out of this set of 4 intersections. So let's imagine that there are, say, 3 cars per minute going there, 5 cars per minute flowing in from that direction, maybe 2 cars per minute flowing in there, 1 per minute there. Maybe there are 2 cars per minute leaving that intersection, and 4 cars per minute that way. And then finally, maybe 2 and 3 cars per minute there. So we know all of these external exits for these intersections. What we don't know are the intermediate flows. Let's say x1, x2, x3, and x4. Now, if we imagine that flow must be conserved within each intersection, that is, that no cars get stuck within the intersection, then each intersection provides us with an equation, right? So equation A says that there are 8 cars flowing in total, 3 plus 5, and that they are flowing out with x1 plus x4. So that gives us the equation x1 plus x4 equals 8. Let's look at B. Okay, we have x1 flowing in, x2 flowing in, and 2 plus 4 equals 6 flowing out. So therefore, we can write x1 plus x2 equals 6. In intersection C, we have 2 plus 1, 3 flowing in, x4 also flowing in, x3 flowing out. So we could say x3 minus x4 needs to equal 3. And then finally, intersection D, we need to have 3 flowing in, x3 is flowing in, x2 is flowing out. So x3 minus x2 needs to equal 5. Now let's write this in our matrix form. We have equation A, we've got a 1, a 0, a 0, and a 1, and then an 8. Equation 2, we have a 1, and a 1, a 0, and a 0, and a 6. Then we have 0, 0, 1, negative 1, 3. And then 0, negative 1, 1, 0, and 5. Now let's take this and put it into reduced row echelon form. We'll come over here. Step 1, I'm going to subtract the top from the bottom in order to get rid of that guy there. So I'll write the first row as usual, subtracting that off, subtracting the first row from the second row. I get a 0, and a 1, and a 0, and a negative 1, and then a negative 2. And then I'll leave the rest there. Now, I see the third row is already conveniently done for me, so I can move on to the fourth row where I'm trying to get rid of that negative 1, and I'm going to do that by adding the second row to it. So, as before, and 0, 1, 0, negative 1, negative 2. Now I'm going to add those up, and I get 0, 0, 1, negative 1, 3. Okay, that's progress. But now I notice that row 3 and row 4 are identical. And so if I were to reduce further, when I try to do that last step to get rid of that one, what's going to happen is I'm going to wind up with all zeros along that side. So I'll wind up with a row of zeros. So this means that the problem is under-constrained. There actually aren't enough equations to determine uniquely x1, x2, x3, and x4. There are an infinite number of solutions. In this situation, The book describes a thing called the -1 trick, which from our point of view corresponds to taking this column here and putting in a -1. And then solutions will be scales in this case of that column. So what that means is that our space of possible solutions to this are lambdas multiplied by 1, -1, -1, -1. So what does that mean in terms of the traffic flow? So lambda can be anything. So if we look at that, we see that a positive number in 1 corresponds to flow this way, negative number in 2, flow this way, negative number in 3, this way, negative number in 4, this way. And you can see that there is actually a kind of redundance in this network. So just to be clear, the arrows are indicating the sign convention. They're not indicating that these are one-way streets. And so what can happen is that we can have an arbitrary number of cars flowing around the middle, or perhaps if this lambda were negative, they would be flowing backwards against this arrow, but they would not be participating in any of the numbers around the perimeter. And so the actual values of x1, x2, x3, and x4 can be scaled up or down in addition to needing to explain all of the numbers along the side, and they have one additional degree of freedom, which is that scale. So this is an example of an under-constrained system where lambda indexes into the set of solutions that are available.